Good days everyone, my name is Teo Cheng Kiat, 4th year student from UTM, MJIIT, Mechanical Precision Engineering. My FYP title is Dynamic Calibration of Thermocouple. Before we enter into the main topic, what is thermocouple? A thermocouple is a sensor used to measure temperature. This is a basic definition of thermocouple. However, for sensors part, there are two more types of sensor have the almost similar definition to thermocouple, which are RTD and thermistor. And this is how these three sensors looks like. There are several differences among these three sensors, and it will be shown in this table. Thermocouple have the widest temperature range, more accurate data, and more long-term stability compared to thermistor and RTD. Besides, thermocouple require no voltage supply or current supply, unlike the others. Furthermore, it got much faster response time compared to the RTD and thermistor, as well as is very cheap. This is why the thermocouple is widely used in industry and daily life. So, how does a thermocouple work? The working principle of thermocouple based on Seebeck effect. This effect states that when a closed circuit is formed by joining two dissimilar metals at two junctions, which are hot end and cold end. On the hot end part, the electrons got heated and gain energy, thus move to the cold end, and therefore different temperature will be formed at the hot end and cold end. Then an electromotive force (EMF) is induced in this closed circuit. The amount of induced EMF is different from different metal combination and is proportional to the temperature difference of the junction. This is the basic thermocouple working principle. Since my FYP title is about dynamic calibration of thermocouple, there's also static calibration of thermocouple that had been done together with dynamic calibration in the previous research paper. The differences between dynamic calibration and static calibration is whether the physical input will vary significantly along the time or not. For dynamic calibration, it will, but static calibration, it won't. However, for my FYP, I will only do the dynamic calibration of thermocouple by changing the size of the junction of thermocouple and determine the changes of thermal response along the time and note down the result. The result noted down from the experiment will then compare with the simulation result and determine the uncertainty that caused the result to be different. Let's take an example of heating a metal bar and metal board. When we apply heat on the metal bar, the electron of the burning part will get excited and move to the cold part, and thus the heat is transferred to the cold end with fast speed. On the other hand, when the heat is applied on the metal block, it requires more time for the heat to be transferred to the cold end. Right here, we can look into the heat transfer equation, which is rate of heat transfer Q over T equal to rate of conductivity K times surface area A and differences in temperature, which is delta T. So we further look into this equation. Q equal to KAT delta T. With this equation right here, we can conclude that the rate of heat transfer is directly proportional to the area and also time constant. Therefore, we can conclude that when surface area increases, the rate of conductivity will increase as well as the time constant. And it goes the other way around. When surface area goes down, the rate of heat transfer goes down and time constant also go down. So from this small example is much similar to the experiment that I'm going to do. That's all from me. Thank you.